Scene script. Have you ever wondered why ketchup flows freely from the bottle after a gentle shake but remains firm when left undisturbed? This phenomenon is a fascinating example of thixotropy, a term that might sound like it's straight out of a science fiction novel, but in reality, it's a part of our everyday life. Thixotropy is a time-dependent shear thinning property. In simpler terms, it's the ability of certain gels or fluids to become less viscous or thinner when they're shaken, stirred, or otherwise stressed, and then return to their previous, thicker state when left at rest. Imagine a pot of honey or a tube of toothpaste. They keep their shape until we squeeze or stir them, right? That's thixotropy in action. But why does this happen? Well, it's because of the unique structure of certain particles within these substances. When undisturbed, these particles form a loosely bound network that maintains the substance's viscosity. When we shake or stir the substance, this network breaks down, allowing the substance to flow more freely. Once the stress is removed, the particles gradually reassemble their network, and the substance returns to its original state. Now let's step into the broader sphere of rheology, the study of flow and deformation of matter. Thixotropy is just one aspect of this fascinating field that encompasses everything from lava flow to the spread of creams and lotions on our skin. Rheologists are like detectives of flow and deformation, investigating how materials behave under different conditions. So why should we care about all this? Because understanding these principles can help us in various fields, from designing better products in the cosmetic industry to creating more effective medications in the pharmaceutical world. So next time you are shaking that ketchup bottle, remember, you are experiencing thixotropy. Now that we understand the concept of thixotropy, how do we measure it? Well, the answer lies in the use of an ingenious device known as a rheometer. A rheometer is a scientific instrument that measures the flow of liquids or slurries in response to applied forces. It's a bit like a thermometer for viscosity, but instead of measuring temperature, it measures the resistance to flow or deformation of a substance. In the world of thixotropy, rheometers play a pivotal role. They help us understand how a substance changes its viscosity under different conditions. Here we are primarily interested in the shear rate, or how fast the substance is deformed, and the shear stress, or the force applied to deform the substance. A typical method to measure thixotropy involves the creation of what we call a hysteresis loop. Now don't let the term scare you. A hysteresis loop is simply a graphical representation of the difference in the up and down curves of a substance's viscosity as it is sheared and then allowed to recover. Here's how it works. First, the rheometer applies a steadily increasing shear rate to the sample, and we measure the viscosity at each point. This gives us the up curve. Then, the shear rate is decreased at the same rate, and again, we measure the viscosity. This gives us the down curve. The area between these two curves is the hysteresis loop, which represents the thixotropic behavior of the substance. The larger the loop, the more thixotropic the substance is. In other words, a larger hysteresis loop signifies that the substance takes a longer time to recover its initial viscosity after the removal of shear stress. So, as you can see, measuring thixotropy is a fascinating process of applying forces, observing changes, and interpreting graphical representations. And while it may seem a little complex at first, with a bit of practice and understanding, it's all quite straightforward. So, measuring thixotropy isn't as complex as it sounds, is it? Let's dive into the world of rheology, specifically focusing on disperse systems. But what exactly is a disperse system, you may ask? Well, in simple terms, a disperse system is a mixture where one substance, the dispersed phase, is distributed or dispersed in another, the continuous phase. Examples of dispersed systems include emulsions, suspensions, and foams. Now let's discuss rheology, the science that studies the flow and deformation of matter. When we're dealing with dispersed systems, rheology becomes an incredibly valuable tool. It helps us understand how these systems flow and deform under different conditions. It's like having a window into the inner workings of these complex mixtures. Take an emulsion as an example. It's a dispersed system where tiny droplets of one liquid are scattered throughout another. The rheological properties of an emulsion can be influenced by factors like droplet size and concentration, Smaller droplets, for instance, can make the emulsion thicker and more resistant to flow, a property we call viscosity. Similarly, a higher concentration of droplets will also increase the viscosity. Suspensions, another type of disperse system, follow a similar pattern. Here, solid particles are dispersed in a liquid. The size and concentration of these particles can significantly impact the suspension's flow behavior. Larger particles or higher concentrations can lead to a higher viscosity and even cause the suspension to behave like a solid under certain conditions. But why does all this matter? Well, understanding the rheological properties of these dispersed systems can reveal a lot about their behavior. This information can help in the design and optimization of various products, from food and cosmetics to pharmaceuticals and construction materials. So next time you spread some mayonnaise on your sandwich or apply some lotion to your skin, remember the hidden world of dispersed systems and the fascinating science of rheology that helps us understand them. Understanding the rheology of dispersed systems can reveal a lot about the nature of many products we use daily. Now, let's explore how these concepts of thixotropy and rheology are applied in the field of pharmaceuticals. Rheology, the study of the deformation and flow of matter, plays a pivotal role in pharmaceutical manufacturing and product development. It's like the secret sauce that ensures the consistency, quality, and performance of our medicines. Consider a simple tablet, for instance. Rheology is used to understand how the powder will flow during manufacturing, affecting the uniformity of the final product. It also impacts the drug's dissolution rate, a crucial factor that determines how quickly a medicine starts working in our bodies. When it comes to topical formulations like creams and gels, rheology helps in determining their spreadability. It's the science that ensures your ointment spreads evenly and smoothly on your skin, delivering the medication exactly where it's needed. But let's not forget about thixotropy, our other key player. Thixotropy is a time-dependent shear thinning property. Simply put, thixotropic substances become less viscous over time when shaken, stirred, or otherwise stressed, and return to their original viscosity when left to stand. This unique property is exploited in creating better, more effective drug delivery systems. Imagine an eye drop solution. It needs to be thin enough to be squeezed out of the dropper, yet thick enough to stay on your eye long enough for the medication to be absorbed. That's where thixotropy comes in, allowing the solution to change its viscosity based on the stress applied. From injectables that need to flow easily through a syringe, to suspensions that need to maintain a uniform distribution of particles, the applications of rheology and thixotropy in pharmaceuticals are endless. Understanding these principles allows us to create medications that are not only effective but also user-friendly, improving patient compliance and ultimately their health outcomes. The world of pharmaceuticals is indeed fascinating when seen through the lens of rheology and thixotropy. We've journeyed through the intriguing concepts of thixotropy and rheology and their applications in the pharmaceutical world. But what are the key takeaways? Firstly, we explored thixotropy, a time-dependent shear thinning property. Certain gels or fluids that are thick or viscous under static conditions will flow or become thin over time when shaken, stirred, or otherwise stressed. This unique characteristic has a wide range of applications, from everyday products like ketchup and paint to complex pharmaceutical formulations. Next, we dove into the concept of rheology, the study of flow and deformation of matter. It's not just about understanding how liquids flow, but also how semi-solids, solids, and even gases respond to applied forces. It's this science that helps us predict and control the behavior of different materials, including pharmaceutical products. Then we ventured into the world of dispersed systems and their rheology. Dispersed systems such as emulsions and suspensions play a critical role in the creation of various pharmaceutical products. Understanding their rheology allows us to control their stability and performance, ensuring the safe and effective delivery of medication. Lastly, we examined the pharmaceutical applications of rheology. From the formulation of drugs to their manufacture and administration, rheological principles guide every step. They help us create products that not only effectively deliver medication, but also enhance patient compliance. But our exploration doesn't have to end here. These concepts are just the tip of the iceberg, and there's a whole universe of knowledge waiting to be discovered. So we encourage you to dive deeper, explore more, and expand your understanding. Remember, the more we know, the more we realize how much there is yet to learn. So keep that curiosity alive and keep exploring. Don't forget to subscribe for more because you won't find me later. Dive deeper into the world of Thixotropy and Rheology, and you'll uncover more fascinating facts about the world around you.